Hi, my name is Sean Peisert. I'm a computer scientist at Lawrence Berkeley National Laboratory and an adjunct professor at UC Davis in computer science. The talk today that I have for you is about security in high-performance computing environments, and specifically about how emerging technologies and research can advance cybersecurity as an enabling capability in HPC, and not just as a capability that might get in the way of optimal performance or otherwise put up barriers for users of high-performance computing systems. Before I dive into a lot of the technical details, I'd also like to give a little bit more background about myself. So the Berkeley Lab is what we call an open science lab. And so we do a lot of research in open scientific problems of various kinds, environment and energy and elements like that that are very much in the public domain. So high-performance computing, of course, can mean different things to different people, and high-performance computing systems can look somewhat different in different environments. And so I just wanted to let everybody know who's watching this that I view high-performance computing through a particular lens, which is this open science, public facility kind of high-performance computing that I've worked in for the past almost 2 decades, really. The other thing to point out is that, of course, there is high-performance computing in much more closed environments, and so I will try and speak to that to a certain extent as well, because there's applicability of what I'd like to tell you in both. These 2 workshop reports, by the way, are from 2015, and they come out of 2 workshops that I ran in that same year for the Department of Energy Office of Advanced Scientific Computing Resource. And those 2 workshop reports might be of interest for the community in terms of some of the thinking that we've had in security over the past many years. There's many reasons that we care about security in scientific computing. I've put this first bullet up here. This is one of the problems that has become quite prevalent throughout computing. It certainly has not been on the radar for all that long, but ransomware is an issue that has been a growing problem in computing in general, and is becoming a bigger problem in high-performance computing as well. This is really made possible by the rise of cryptocurrencies that allow for anonymous or nearly anonymous transactions of finance. Another problem in the security addresses in scientific computing is protecting integrity of data. Data could be modified, it could be lost, it could be the result of bit flips, equipment failure, or intentional modification. Certainly, one of the problems that people think of most in security is confidentiality, and again, high-performance computing is no exception here. Protecting the confidentiality of data that resides on high-performance computing systems or is computed on those systems from exposure can be a significant concern as well. And I will say that's particularly sensitive data, but even pre-publication embargoed data is data that we don't necessarily want to be exposed prematurely. Sensitive data might include data that's subject to regulation like HIPAA, FISMA, trade secrets, personally identifiable information, and other data that might not be shared due to whatever risks result from its exposure. And finally, one of the things that we worry about in high-performance computing is protecting systems from misuse. So this, if you look at the CIA, or confidentiality, integrity, availability triad, refers to the availability. So somebody who's using the high-performance computing system in a way that it's not supposed to be used, and thereby also preventing someone who should be using the system legitimately from its optimal proper use. And by the way, regarding integrity and confidentiality, I will also point the viewers of this presentation to a handful of reports on the right side of the slide as well that came out of work done by Trusted CI, the NSF Cybersecurity Center of Excellence, over the past couple of years or so. The threats that I am talking about today are not just theoretical. Here I have the news snippets from a number of different threats that actually span several decades. The Cuckoo's Egg is a book that came out of a hack that dates back, in fact, to the 1980s, I believe. More recently, there have been a handful of incidents in which supercomputers have been used to mine bitcoins, again, a cryptocurrency. And that has taken place both in the US and in Russia, and most recently, just last year, in Europe. We might ask, so what are the problems with the existing security models? What are these existing security models? Well, most often, if we are going to provide some sort of data, maybe sensitive data of some kind, to an organization to do some sort of analysis on in a supercomputing environment, we'll do one of a couple of things. One of those things is that we either have a trusted third party, that could be a public computing facility, it could be a third party vendor of some kind, or we are using legal agreements of some kind, saying, you will protect this data in a certain way, or maybe some combination of these two things. The problem is that trusting for an organization's intent, even an organization's legal contract in what they've said that they will do, is simply not enough. And also on this slide here, I'm showing a handful of headlines that show all of the well-intentioned organizations that have tried to protect information and have failed. 22 million people in the Office of Personnel Management database, 145 million Social Security numbers from Equifax, 87 million users from Cambridge Analytica that were exposed. So lots of organizations that say we will do this with your data and have every intention of doing so, but look what happens with these things. These existing solutions, these existing models where we simply say, trust me, this is what I'm going to do, are no longer enough. There's also, just to get back to the theme that I began with in terms of security as an enabling technology, there are many efforts to try and solve large public problems, things that are clearly in the public sphere that cannot be solved under a lot of current models as well. So all of these are papers and articles that reflect desire to improve public way of life, public policy, climate science, the navigation to reduce drive time, to reduce overall carbon emissions during traffic and commute hours. All of these things require different types of public data. COVID-19 vaccines have relied on the results of clinical trials. Improving navigation in urban areas requires looking at vehicle mobility patterns. That includes publicly identifiable information. There are so many things that either result in a loss of personal privacy, that result in a loss of trade secrets, that we are becoming reluctant to share for good reason, because privacy and confidentiality are actually very important to individuals, organizations, governments, companies, whatever they happen to be. And so the question becomes, how do we solve the world's problems without this data? Well, right now, the answer is maybe we're not doing it very well. We're trying to solve problems on isolated data sets, on data sets that are too small, maybe biased as a result, and we're not getting very optimal scientific solutions in some cases as a result. So we really need solutions that leverage the right approach to allowing us to make the optimal use of this data while simultaneously protecting the confidentiality and privacy of the underlying data that we're using. And a lot of this talk is really about the point that security and privacy techniques that are properly used can help solve these problems. So the question is, how do we do secure high-performance computing? How do we compute with large amounts of sensitive data, regulated data, proprietary data? I mentioned vehicle location data, smart meter data, smart city data. And in fact, how do we protect from both external and internal threats? So data providers don't have to place as much trust in data centers. Data analysts don't have to place as much trust in data centers. Data providers don't have to place as much trust in data analysis. How do we improve the trust model so that we don't have to trust both the competency and the intent of quite so many individuals? And how do we do so for both integrity of the data and confidentiality? One existing approach is to attempt to remove sensitivity of the data. And so in a situation like this, we might have data that describes different patients within a healthcare data set. And we will take that data and try and make it more general. Instead of having an individual's name, we might replace that name with a unique number. Instead of having an exact date, maybe we'll replace that date with just a year, or maybe just a month and a year. And so this is a traditional or classical approach for anonymization or sanitization by either enforcing regularity by removing specific aspects, or masking by concealing or pseudonymizing certain aspects. The trouble is that we have actually shown time and again that through inference attacks by linking to external data sets, typically, or other external sources of information, anonymization really doesn't work. And there's a couple of references I've shown here at the bottom that are great references if you want to dig into this more. Anonymization can work in some cases, but more often than not ends up either removing too much or too little information. But once the data is out there, it's impossible to retract it. And so we typically err on the side of over-anonymizing, which then can reduce the usefulness of that data for the research purpose that we might want to use it for. Another existing approach is trust via physical protections. And in a situation like this, we have a compute system that might literally be what's called air-gapped, so it's not connected directly to networks that go onto public internets, and it's in a closed individual environment in which a researcher might literally go behind a guard gate into a locked windowless building to access the data where nothing goes in or out. The trouble is, most scientific researchers certainly aren't used to working in this kind of an environment, and typically are unwilling to work in this kind of environment on a very regular basis. And so something like this, while perhaps possible and perhaps used in some circumstances, certainly isn't optimal for rapid advances in science, in which we're trying to make a system as useful as possible to researchers, and perhaps as close as possible to the environment that's optimal for the way that they conduct their research. Again, probably not just on their own, but with large international collaborations with their postdocs, with their grad students, with their collaborators, and so on. So to summarize, a lot of existing solutions focus on physical system isolation, which can be effective from a security perspective, but less effective from a usability perspective. They also help protect against external threats, but not necessarily internal threats. If your system administrators still have access to the data, that means that the system administrators or anybody else with physical access to the system in which the data is stored on computed on, they could still be involved in some sort of data manipulation or data exposure. And so the summary is that both high-performance computing systems and, frankly, cloud systems currently require full trust of both the computing center and the system administrators. So one question that we might ask is, how do we protect confidentiality and integrity of large data sets against both external and internal threats in a usable way? When we think about high-performance computing, there are actually some challenges and opportunities that help us address this problem. So there are some similarities between HPC and traditional IT. They're both connected to IP networks. They often run Linux-like operating systems. But HPC is also distinctive in certain ways. And again, there's challenges and opportunities here. A challenge is that HPC still requires high performance. It does high-performance computation and data transfers. A potential opportunity is that high-performance computing systems tend to run highly exotic hardware and software stacks. A challenge, again, is that HPC systems are often extremely open, include international collaboration. So this air-gap solution often is not one that is appropriate. And in fact, we can't even use certain security solutions, such as network firewalls, in the same way because of the way they affect the performance of high-throughput network transfers. As I mentioned on the previous slide, all of these exotic hardware and software stacks, though, can be an opportunity. What this means is, in fact, all of these different elements could be modified to add HPC-appropriate security in the same way that they've been modified already to add HPC-appropriate performance. And one of the solutions that we have been exploring at the Berkeley Lab and also with my collaborators at UC Davis have been an element called trusted execution environments. So trusted execution environments, or TEEs for short, enforce strong separation from other processes. Some of them can encrypt memory and computation and can prevent exposure to other users and even system administrators. So the idea behind TEEs is that they can enable a data owner to share data without actually even having to trust the compute facility. So given the appropriate architecture, TEEs can enable strong security in HPC involving sensitive data. So this entire threat model of a data provider having to trust the data center completely gets broken down with this, because the TEEs, by encrypting memory and isolating from other users and even from system administrators, doesn't require that trust anymore. And trusted execution, it exists today. CPU manufacturers such as Intel and AMD and ARM all make chips now that support some variation of TEEs. Intel perhaps is the best known with their SGX, AMD with secure encrypted virtualization and several variations on that, and ARM with TrustZone. In addition, we're seeing a number of open source hardware implementation of TEEs, perhaps notably including the RISC-V-based Keystone environment from UC Berkeley. And perhaps most importantly, in a nod to confidence of the use of TEEs, we are now seeing, I think, all of the major cloud environments, including Google and Amazon and Microsoft, implementing confidential computing based on different T-like technologies. There's also a Linux Foundation project called the Confidential Computing Consortium that is expanding the development of TEEs as well. My collaborators and I have actually explored commercial TEEs for their appropriateness to high-performance computing. And we started by looking essentially at the usability of these systems and what are they designed for. What we found, at least in the initial iteration of AMD's SEV, was that the early implementations of SEV did not focus very much on integrity. There's some more current implementations that do. SGX did. The trusted computing bases for SEV was also a lot larger, whereas Intel SGX has a somewhat smaller trusted computing base and requires programs to be partitioned in a certain way to use the technology. AMD's SEV allows you to run unmodified programs, so no application changes required. But as a result, you have to trust the entire guest operating system and anything running in it. The good news about SEV was that you can use all of the available RAM, but again, SGX limits you to 94 megabytes of usable memories, which for HPC is pretty small. So what we found was that there were some pretty key differences right off the bat with what you have to do to your programs in order to use these systems and how these systems could be usable. We then took this a step further by running some benchmarks. We evaluated both some traditional modeling and simulation benchmarks, notably the NAS parallel benchmarks, as well as some more modern data-driven benchmarks, one involving a graph analysis and some other modern machine learning and other similar workloads for modern data-driven HPC as well. What we found in our result is, not unsurprisingly, Intel SGX as currently implemented is not appropriate for HPC. It slows down as much as, in some cases, a small amount to as much as 2 orders of magnitude or more compared to unsecure execution. And this is very much as a result of both some low-level architectural elements, as a result of the simple fact of the matter that you only have 96 megabytes of usable memory. On the other hand, we found that AMD's SEV can be performant for scientific computing, but it's limited in HPC due to the virtualization overhead, lack of secure low-latency multi-node communication, and the fact that currently it only supports CPUs, does not support GPUs or other sorts of accelerators. Although that is something that we gather that a number of different vendors and cloud providers are working on down the road. I will say these results appear in a IPDPS 2021 paper from this year. So my collaborators and I are looking at developing new secure architectures for high-performance computing that overcome some of the limitations of existing solutions. Number one, we'd like to address secure multi-node communication. Right now, if you have to communicate via ordinary SSH over TCP, it simply imposes such a high latency that the throughput declines dramatically, and traditional HPC involving multi-nodes simply doesn't work very well. Second, we'd like to be able to reduce the virtualization overhead. So while the enclave itself doesn't impose a significantly higher overhead on the computing than it does without the enclave, the virtualization itself still imposes enough overhead. So how do we overcome that issue in a way that still addresses the security benefits that we get from virtualization on, say, an SEV-type environment? And finally, how do we address heterogeneity? Architectures that use Ts, but also enable us to use GPUs and accelerators in this secure way, in the same way that we use CPU-based Ts. So as part of our exploration and development process, we are building on the RISC-V-based Keystone T and are leveraging the Keystone runtime and compiler elements as a starting point, and also building on existing high-performance computing OS runtime and compiler and programming language elements as a starting point as well, and trying to figure out how to map these things together. There's lots of open questions we still don't have the answer to, but we're trying to make progress on this, since this seems like an extremely important and vital solution that the community needs. Some of the open questions we're looking at include, to what degree do existing architectures satisfy the needs of the HPC-T? So we're digging deep into Keystone on this. What should the threat model be? What should the user programming model be? Should we force the user to redevelop their architecture in the way that they use MPI or OpenMP already to do their development? What happens if they don't modify their program at all? How does that change the trusted computing base? What should be in the trusted computing base? How do we figure out secure multi-node communication? How do we expand Ts to heterogeneous architectures? And how do we handle attestation at scale? In other words, the ability of any user to know that they're running inside a secure computing environment. How do you scale that up to not just a single node, but potentially hundreds or thousands of nodes that you're all trying to do remote attestation with at scale? We don't have the answers to many of these questions yet, although we're exploring them. And to do this, we're using a co-design approach. We are leveraging the Gem5 environment that we can use to do design space exploration for a number of different types of architectures. So Gem5 is a framework that provides processor models, cache subsystems, and memories for a whole bunch of different instruction set architectures, which also include, as of recently, RISC-V. It's also been used to analyze a number of security vulnerabilities as well, including Spectre Meltdown. So we can not only explore what it would look like to examine and implement our different high-performance computing T architectures from a performance perspective, but we can examine them from a security perspective as well. One of the reasons we chose Gem5 is because there's some existing tools like QEMU that are functional level modeling that can be fast, but don't necessarily give us detailed timings. And cycle exact models that we might implement would give detailed timing, but could be hard to modify and slow to simulate. So we actually, as of recently as well, have built on the existing RISC-V implementation in Gem5 and also implemented Keystone as well. And so this CARV paper, which was presented recently in June, discusses the implementation of Keystone and the execution of that in Gem5 as well. And as you can see in this slide, the results are pretty similar to the expected results that were published in the original Keystone paper. And so we feel pretty confident that the simulation is an accurate and effective way to explore some of the design choices that we might want to look at in this environment. This is another example that shows, again, some of the different results that also includes discussion of different encryption latencies should memory and computation also be encrypted during memory. And again, the results show the simulated results being fairly close to the expected results as demonstrated in the original Keystone paper as well. Here are a handful of recent publications that present our work. And I just wanted to conclude by saying that it's our goal to enable computing of data in high-performance computing environments in a more secure manner, in a way that does not require trusting the system administrator to administer the system in a particular way and not simply log in as a system administrator and potentially manipulate or expose data intentionally or accidentally. It's our goal to enable the preservation of data by maintaining the integrity of data in a high-performance computing environment as well, in a way that data also can't be manipulated by other users or system administrators. And it's important to do this, of course, in a way that's appropriate to high-performance computing. So this is done in a way that is conscious and cognizant of performance and supports performance as a first-order goal, and at the same time does so in a context that is cognizant and conscious of the threat models of high-performance computing environments, which are very different and distinct from other environments. If you have sensors in a field, if you have a desktop, you'll develop things in a very different way than HPC. And so our goal is to try and develop systems that support simultaneously the security and performance and usefulness goals of high-performance computing as well. Finally, I'd like to acknowledge my amazing collaborators who have contributed large portions to this work. Ayaz Akram is a graduate student who did most of the heavy lifting of this work that you see here. Venkatesh Akela and Jason Low-Power are professors of computer science at UC Davis and have been my partners on this work. I'd also like to acknowledge the Office of Advanced Scientific Computing Research at the U.S. Department of Energy for supporting this work, and thanks to them. Thank you for your time today.